The true risk of machine learning model H is the expectation of its random loss. To calculate it, we need to know the joint distribution function of input and output data. In practice, it's usually unknown, and we estimate the risk using available data sample. This estimation is called as empirical risk. The empirical risk can be calculated over training, validation, and test samples. And we ask, which of these estimates is good one? The empirical risk over training sample is too optimistic estimate because we've trained the model using this sample, but we have minimized this risk during the training. The empirical risk over validation sample also isn't fair estimate because we've used it in the training process. For example, we've chosen the model with minimal validation error among various trained models. The empirical risk over test sample only remains. It looks as a good estimation, but there is a problem. We have only one value of this error, and we don't know how random it is. And nothing tells us about how sensitive this error is to the particular training and test samples. If we had some sample of test errors, we could estimate its statistical properties and so would be more conscious about the risk of the trained model. But how can we get the sample of test errors? The solution might be the following. We repeatedly partition the available data into training and test samples. Every time we train the model on the training sample and calculate the error on the test sample. As a result, we obtain the sample of test errors. This idea is the basis for a model evaluation technique called as cross-validation. There are several cross-validation techniques. It's Monte Carlo, K-fold, holdout, and leave one out cross-validation. Sometimes the resubstitution is also considered as a cross-validation technique, but it's a trivial case of cross-validation when the training data itself is used for validation. In Monte Carlo cross-validation, the original data is divided into training and test samples k times. Each time, the training and test instances are chosen randomly with the given proportion. For example, 70% for training and 30% for test. As a result, we obtain k-trained models and k-test errors. The disadvantage of Monte Carlo cross-validation is that there may be the case when some instances will be included only in the training or test samples, or won't be included neither in training nor test samples. This drawback eliminates the k-fold cross-validation. The origin data is divided into k equal parts. In every experiment, all parts except one are used for training and the remaining part for test. So it's guaranteed that all instances will be in the test sample only once. As a result, we obtain the sample of k-test errors. Leave one out cross-validation is a particular case of k-fold cross-validation, when k is equal to origin sample size. It's useful when the sample size n is small and we would like to use as much data as possible for training. The disadvantage of leave one out cross-validation is its high computational cost because we need to train the models n times. The simplest cross-validation technique is holdout cross-validation. We partition data into train and test samples only once, and train the model on training sample and test it on test sample. As a result, we obtain only one test error. By partitioning data into training and test samples, we should be aware of the following problem. Suppose we have an unbalanced classification problem where one class takes, for example, 1% of all data. And if we partition the data randomly, it may turn out that this class won't be represented in all parts. It's undesirable. And to guarantee that all classes will be represented in all parts, the so-called stratification is used. In practice, the stratified sampling is performed as follows. We take data from each class separately and partition them. In this way, all classes will be represented in all parts, keeping their proportion. As a result of cross-validation, we receive the sample of test errors. We can calculate its mean and variance. The perfect case is when the mean value is acceptable and the variance is close to zero. It means that the model is not sensitive to the particular training sample and has a good generalization capability. In this case, it doesn't matter which of the models trained during the cross-validation can be developed. Moreover, the new model can be trained using all available data. Because we are sure that the model has good generalization capabilities, we know accurate estimate of its risk and it doesn't depend on the particular training and test data. When we use multiple training sets and obtain multiple trained models and the sample of test errors, we in fact evaluate a learning algorithm used, no individual learned model. And as soon as we are sure in the training algorithm, we can apply it to any training sample and obtain a good learned model that has acceptable risk. The cross-validation can be used not only for test sample, but also for validation sample. In this case, it's called as internal cross-validation. For example, we can use holdout cross-validation to partition data into training and test sets. And inside the training set, we use the k-fold cross-validation to partition it into training and validation sample. Or vice versa. The external cross-validation technique can be, for example, k-fold, and the internal can be holdout.